Imagine a universe where everything, from the smallest particle to the vastest galaxy, is made of vibrant cosmic strings. Welcome to string theory, the most ambitious candidate for a theory of everything. A vision that not only unifies the fundamental forces, but also projects us into a realm of hidden dimensions, parallel universes, and a reality far more complex than we can imagine. In this video, we will delve into the fundamental concepts of the theory, its fascinating history, the challenges it faces, and its incredible implications for our understanding of reality. If you are passionate about science at the frontiers of knowledge and appreciate the effort I put into exploring such complex topics, subscribing to the channel would help me enormously to continue creating content like this. Thank you. At the heart of the theory is a revolutionary idea. The fundamental building blocks of the universe are not point-like particles, but tiny one-dimensional filaments of energy called strings. They are incredibly small, hundreds of billions of times smaller than an atomic nucleus. It is estimated that they measure approximately the Planck length, which represents the smallest length at which current laws of physics still make sense. These strings can be open with ends or closed, like rings, and they can unite and separate. The magic lies in their vibrations. Just as the different vibrations of a violin string produce different musical notes, the different vibrations of these fundamental strings give rise to everything we know, particles and forces included. An electron, a quark, a photon are all manifestations of a string vibrating in a specific way. The mass of a particle is determined by the energy of its string's vibration. More energy, more mass. And since mass is related to gravity, gravity itself naturally emerges from the theory. The graviton, carrier of the gravitational force, is a string that vibrates at the lowest frequency. This extensive nature of strings solves a fundamental problem: the incompatibility between general relativity and quantum mechanics. At tiny scales, space-time is a seething cauldron of quantum fluctuations, and strings, not being points, are as if they smooth out these fluctuations, attenuating them just enough to make the theory coherent and unified. This capability is the key mechanism by which string theory reconciles general relativity with quantum mechanics. One of the most fascinating and counterintuitive aspects of string theory is that its mathematics requires the existence of additional spatial dimensions beyond the three we perceive and the temporal dimension. Initially, there was talk of 6 extra dimensions for a total of 10 space-time dimensions. Subsequently, this number increased to 7 extra spatial dimensions for a total of 11 space-time dimensions. But why are they necessary? Without these dimensions, the equations of string theory would lead to mathematical inconsistencies, such as anomalies or the prediction of hypothetical particles traveling faster than light, making the theory unstable and unrealistic. The quantum consistency conditions of the theory require a specific number of dimensions for the strings to vibrate coherently, without generating paradoxes. And this is where another crucial pillar of string theory comes into play: supersymmetry. This elegant idea postulates that for every fundamental particle, there is a superpartner with different spin called a sparticle. For example, the electron would have a bosonic superpartner called selectron, and the photon a fermionic superpartner called photino. Supersymmetry not only makes string theory even more stable and coherent, helping to cancel annoying mathematical divergences, but also solves important problems such as the stabilization of extra dimensions. Although these superpartners have not yet been observed, their existence is fundamental for many of the most promising extensions of string theory, and they are ideal candidates for dark matter. But why aren't these extra dimensions observable or detectable in any way? The idea is that they are very well hidden through the phenomenon of compactification, an idea revisited by Kaluza and Klein. Imagine ants walking on a long, narrow rope. From a distance, the surface appears one-dimensional, like a single line. But if we observe it up close, we realize that the ants can also walk around the circumference of the rope. There is thus a new dimension, much smaller, which was not appreciable from a distance. This is the idea of Kaluza-Klein. Our three spatial dimensions are large, while the extra ones are so small and curled up as to be invisible. The substantial difference compared to ants is that we humans are too large to perceive the existence of these dimensions, so we live without even the slightest perception of such a hidden reality. And to further complicate the situation, these could be so small as to escape our detection, even with very sophisticated instruments, at least until today. The geometry of these compactified dimensions directly influences how strings vibrate and consequently the properties of the particles we observe. Another possibility is the Braneworld scenarios. Here, our universe is a three-dimensional brane, a sort of membrane, immersed in a higher dimensional space, the bulk. Standard particles and forces are confined to our brane, but gravity, mediated by closed strings, can propagate in the bulk. This could explain why gravity is so weak compared to other forces. The brane vision also paves the way for alternative scenarios for the origin of the universe, such as the ekpyrotic model, where our cosmos is born from the collision of two branes in a higher dimensional space, suggesting a cyclic universe of creation and destruction. But to better understand how we arrived at such revolutionary concepts, let's take a leap into the past and briefly analyze the crucial points of the genesis of this theory. String theory has a fascinating history. Born in the 1960s as an attempt to describe the strong nuclear force, with Gabriele Veneziano discovering an equation in 1968 that unexpectedly describes string vibrations. In 1974, Joel Shirk and John Schwartz reinterpreted the theory, identifying one of the string's vibrations with the graviton, transforming it into a potential theory of gravity. Then, in 1984, the first superstring revolution occurred. It is demonstrated that the theory is mathematically coherent without anomalies, and supersymmetry is incorporated. Calabi-Yau manifolds are discovered to compactify extra dimensions. In 1995, the second superstring revolution takes place. Edward Witten proposes theory, unifying the 5 existing superstring theories and supergravity in a single framework. Subsequently, Joseph Polchinski identifies D-branes, extended objects on which strings can terminate, which prove crucial for the theory. Today, string theory remains an extremely active and dynamic area of research in theoretical physics. It is considered the most promising candidate for a theory of everything, thanks to its intrinsic ability to unify gravity with the other fundamental forces. However, despite its mathematical elegance and its great potential, the theory faces significant challenges, particularly regarding experimental verification and its ability to make unique predictions about our universe. The dimension of strings and extra dimensions are so minuscule that direct verification is impossible with current technology. The required energies are astronomical, far beyond the reach of accelerators like the Large Hadron Collider. Furthermore, string theory allows for approximately 10 to 500 different ways to compactify extra dimensions. Each compactification corresponds to a different universe with different physical laws, making unique and falsifiable predictions about our universe difficult. Another important point is that the most direct prediction of the theory for the value of the cosmological constant is enormously larger than the observed value, a discrepancy that should make us reflect. Some critics also argue that the theory is not falsifiable, as it does not make precise predictions at accessible energies. Despite these challenges, research continues. The Large Hadron Collider seeks indirect evidence, such as the creation of particles that would support supersymmetry. It also searches for microscopic black holes or an imbalance in transverse momentum, which would indicate the existence of extra dimensions. Furthermore, physicists use theoretical methods to test the coherence of the theory. Recent studies have shown that the only solution to the bootstrap equations is the extensiveness of Veneziano, suggesting that string theory could be an inevitable description of the universe. The potential of the theory is enormous, as are the profound implications for our worldview. The theory even offers new perspectives on the origin of the universe, proposing alternative scenarios, such as the idea that it arises from the collision of two branes in an infinite cycle of creation and destruction. Some interpretations predict that our universe is only one among countless other parallel universes, each with potentially different physical laws. String theory also suggests that space and time may not be fundamental, but rather derived and emergent structures from the collective interactions of strings, a radical reconceptualization of the very fabric of reality. In conclusion, the string theory is a monumental intellectual undertaking, a bold attempt to unravel the deepest secrets of the universe. It forces us to imagine a reality where space and time emerge from the vibrant dances of tiny strings. It projects us into a multiverse of infinite possibilities, where our cosmos is just a bubble in an eternal expansion. If true, it would imply a revolution in our understanding of the origin of the universe and a reconceptualization of the very nature of reality. The road is still long, full of mathematical and experimental challenges, but the search for a theory of everything continues, driven by human curiosity and the conviction that, beyond what we perceive, there exists a fundamental harmony that links every aspect of reality. String theory is our most promising melody in this cosmic symphony. I hope this journey to the frontiers of science has fascinated you. If you want to continue exploring the mysteries of the universe with me, don't forget to subscribe to the channel, leave a like, and activate the bell to not miss the next videos. Thank you and see you next time.